Dear students, welcome to this online class. Today we discuss about the second part of UV visible spectroscopy, that is applications of UV visible or electronic spectroscopy. Before we go into the applications, let us get familiar with some important terms associated with UV visible or electronic spectroscopy. Already in the previous class we have learned about two terms, that is absorbance or optical density, another one that is epsilon, that is molar absorption coefficient or molar extinction coefficient. These two terms appear in the law which we learned in connection with UV visible spectroscopy, that is Beer-Lambert's law. What is the mathematical expression of Beer-Lambert's law? Absorbance A is equal to log I0 by I, that is the definition of absorbance, and that is equal to epsilon Cx, right? So A is absorbance, which is logarithmic term. It's a logarithmic term. It's log of I0 by I, where I0 is the intensity of incident radiation, and I, or we write Ix also, that is the intensity of the transmitted radiation. And epsilon is a constant which is called molar absorptivity or molar absorption coefficient. And one more term we have learned in the previous session is a somewhat reciprocal of absorbance, that is called transmittance, which is defined as I by I0. It is not exactly the reciprocal of absorbance because this is a logarithmic term, but this is not. Transmittance is only I by I0. So that we can write the relation between absorbance and transmittance as A equal minus log T, right? Okay. Now we move on to some new terms, starting with the first two, that is what is lambda max and epsilon max. See, when we look at the electronic spectra of a molecule, it looks like this. Generally, electronic spectra or UV visible spectrum is plotted between wavelength lambda against intensity or absorbance or intensity in terms of epsilon, right? This is a normal practice. And UV spectrum looks like this. It is very broad. You know the reason that we have discussed at the beginning of this module, because electronic transition necessarily is accompanied with vibrational as well as rotational transition. That's why the spectrum, the spectral peak is not sharp but broad. Now here we can note two important values from this graph. That is, one is this value and the other is this value. We call this as lambda max. So that is lambda max. Corresponding to lambda max, we have an epsilon value that is called E max. So what is lambda max? See, when we pass UV visible radiation to an absorbing medium or a molecule, it absorbs a range of wavelength from the radiation, and lambda max is the wavelength of maximum absorption. See, this is the intensity of absorption, a maximum absorption, the peak of the curve corresponding to this wavelength. This is called lambda max, wavelength of maximum absorption. And epsilon max is the epsilon value corresponding to lambda max, the intensity corresponding to lambda max. Okay, so when we have a UV visible spectrum of a molecule, we figure out these two values from it. Now coming to the next two terms, we have like a pair of terms. Next is, what is chromophore and auxochrome? Chromophore. Chrome means color. Chromophore we can simply call it color producing group. Color producing group. What is a chromophore? See, in an organic molecule if you take, there are different types of functional groups like nitro group, aldehyde group, keto group, etc. We can divide or classify various functional groups into two types. One is chromophore. So the groups like, let me put example, like this vinylic alkene type vinyl group or acetylenic alkyne groups. Let me write nitro group NO2, aldehyde group CHO, keto group acid group, then nitrile group, etc. These functional groups, what is the speciality? All of them contain pi bond or multiple bonds, one or more. So that they will have pi to pi star transition, and also if there are heteroatoms like oxygen, nitrogen, they will have n to pi star also. That correspond to very small energy gap, and UV visible absorption will come above 200 nanometer. So chromophores are those functional groups which are unsaturated and have characteristic absorption above 200 nanometer. That is what is chromophore. So I repeat, chromophores are those functional groups which are having multiple bonds or pi bonds and characterized and they possess or they have characteristic absorption above 200 nanometer in UV visible spectroscopy. Now coming to the second type, that is oxochrome. What is oxochrome? Oxochrome we can simply call them color strengthening group. I will tell you why this name, color strengthening group. Okay. Putting examples here. See, functional groups like OH, that is alcohol or phenol, then OR, that is ether group, NH2 amino group, and various amines like primary, secondary, tertiary amines, etc. Then also halogen. What about these functional groups? They do not have pi bonds or they are not unsaturated, but the speciality is that they all contain heteroatoms and they have lone pairs, one or more lone pairs. All of them has lone pair, right? At least one lone pair. Now these functional groups are called oxochrome. Their speciality is that they contain lone pairs, and an important thing is that they do not have absorption above 200. So they do not have absorption above 200. Do not have characteristic absorption above 200 nanometer, right? So that's their specialty. So these are having characteristic absorption above 200. These are not having absorption above 200. Why they are called color producing and color strengthening group? Let me put an example. Look at this organic molecule. Let me write it here. Okay, this is phenol, right? Phenol, and OH group is there. OH group is an oxochrome. You know that phenol is a colorless liquid. It's colorless. But if we change OH by NO2, that is nitro group, what is this compound? Nitrobenzene, isn't it? Nitrobenzene is having slight yellow color. What's the difference? Here it is nitro group, which is having characteristic absorption about 200. Of course, this benzene ring has its own UV visible absorption, but presence of NO2 make it colored. So it's a color producing group. And if OH come along with NO2, actually regarding oxochrome, we should understand a point more, that they do not have characteristic absorption about 200, but when they come along with chromophore, they will increase the lambda max value. They will increase the absorption wavelength. That is a speciality. That means if we substitute one OH group in nitrobenzene, it will become more colored. Intensity will increase. That means absorption, wavelength of absorption will move more to the visible region or more to the right. Okay? Because whenever oxochrome comes, there will be more conjugation due to the lone pair. Whenever conjugation increases, energy gap will decrease. That's the point. Whenever conjugation increases, energy gap between the lower level and higher level or homo-lumo gap will decrease. When energy decreases, wavelength will increase. So the absorption move from UV to visible, and in visible from violet into red side. So the color intensity will increase due to the presence of oxochrome. So that's about these two terms. Now coming to another set of terms which is regarding shift in the value of lambda max and Emax. For a molecule there will be a characteristic lambda max and correspondingly an Emax, but the value will change by changing the conditions, like if you change the functional groups, if you change the solvent, etc., the lambda max and Emax value of compounds will change. So when there is a change in lambda max, we use some operational terms. It's very easy to understand. Let me write like this. See, lambda max and epsilon max. Okay. When there is increase in the value or decrease in the value. So there are two types of shifts. Either the value may increase or decrease. Okay. See, when lambda max of a compound increases due to various factors, the phenomena is known as bathochromic shift. You should remember the terms. What is bathochromic shift? Bathochromic shift, or it's also called red shift. Let me put an example. See, let me write here benzene. Its lambda max value is equal to 255 nanometer. Okay. Now, when you introduce an amino group here and make it aniline, see, it's an oxochrome, right? Of course, conjugation, this lone pair will come in resonance, and conjugation increases, homo-lumo gap will decrease. For aniline, the value is coming to be 280. So what happened here? Lambda max value increased. This phenomena is called bathochromic shift. So what is bathochromic shift? Increase in lambda max value. Sometimes lambda max may decrease due to some reason. For example, to aniline, if you are adding HCl, that means this is base, amines are basic because of the lone pair on nitrogen, and you are adding HCl. So H plus will attack this nitrogen and it will now change into, it get protonated, but it becomes NH2 will become NH3 plus, right? Because the lone pair will be taken for this H plus to bond and it become NH3 plus. Now there is no more lone pair. Interestingly, the lambda max value of this compound is found to be 254 nanometer. What happened? From aniline it has reduced, decreased, because lone pair is no more there. So the extended conjugation is lost and lambda max reduced. This phenomena is known as hypsochromic shift. The opposite, hypsochromic shift, or otherwise called blue shift. Why this red shift and blue shift? In VIBGYOR, in visible region or visible spectrum, red light is correspond to higher wavelength. That means lambda increases. And blue correspond to violet blue side is having lower wavelength. That means indicating that lambda max has decreased. Now finally, another pair of terms regarding the change in the Emax value. Suppose Emax, epsilon max or intensity of absorption of a compound is increasing, the term used is hyperchromic shift. Hyperchromic shift means increasing Emax of a compound. Its opposite will be what? This is the terminology which we generally use, hyper and hypo, right? Hypochromic shift, where the Emax value decreases. Putting an example, phenol, right? OH. The Emax value of phenol is 6200 centimeter inverse. That is the Emax value. On adding base, you know that phenol is acidic. When you add a base, NaOH for example, this get neutralized and it become a sodium salt, sodium phenoxide, or in effect it become O minus. Electron density increases here, and what happens is that the Emax of this molecule comes to the value 9200. It has increased. Intensity of absorption will increase. This is called hyperchromic shift. And if intensity decreases, the phenomena is called hypochromic shift. An example here is similar to phenol. If you take benzoic acid and it is basified, to benzoic acid you are adding NaOH, for example, a base is added, it will become benzoate ion, CO minus. In this case, it's found that the intensity is falling, where it is 11,600 centimeter inverse here. On basifying, on adding a base, it reduces to 8,900 centimeter inverse. So we have used 4 operational terms to indicate the change in lambda max due to various reasons. So increase in lambda max is called bathochromic or red shift. Decrease in lambda max is known as hypsochromic or blue shift. Increase in Emax is called hyperchromic shift, and decrease in Emax is called hypochromic shift. Right? Now finally we go to the applications of UV visible spectroscopy. Some important applications. See that UV visible spectroscopy or electronic spectroscopy has wide applications in organic chemistry, inorganic chemistry, as well as quantitative analysis, starting with applications in organic chemistry. Applications in organic chemistry. Let us cite a few examples. Number 1, to identify compounds. We can identify compounds by UV visible spectroscopy. Identification of compounds. For example, you take 2 compounds, that is, one is benzene and the other is naphthalene. How can you distinguish or identify these 2 compounds using UV visible spectroscopy? It's so simple. You can measure the lambda max of the 2 and you can correlate which will have larger lambda max. Definitely naphthalene. Naphthalene will have higher lambda max than benzene. Why? Because there is more conjugation. So note this point. Whenever conjugation increases, there will be a red shift. Lambda max will increase because homo-LUMO gap will decrease. That's why. So noting the lambda max value, we can identify compounds. Now coming to the second application, we can identify geometrical isomers to distinguish geometrical isomers or cis-trans isomers. Geometrical isomers. For example, look at this. I am writing a compound that is still B, which has two isomers, cis and trans, geometrical isomers. Still bean is this, having two benzene rings. Okay. You can see similar groups are on opposite side. So this is the cis trans form, and it will have a cis form also. Cis form, you know, it comes like this. This is the cis form. How can you distinguish these two isomers using UV visible spectroscopy? It is by noting the lambda max value only, which will have greater lambda max. This will have greater lambda max. Trans isomer will have greater lambda max as well as E max. It is because in trans the two benzene rings are away from each other. There is no steric crowding. Here there will be steric crowding between these two rings on the same side. So because of that, the two rings, to get rid of this strain, they will remain out of plane. When they are out of plane, you can see that there is large extent of conjugation here, extending over a large distance like this. Okay, so it is this delocalization which gives it a very, very large lambda max. So this conjugation resonance phenomena takes place effectively in trans isomer, not in cis, because in cis these are crowded and they will be out of plane. When the rings are out of plane, then the resonance phenomena will not be effective. So lambda max will be more for trans isomer, right? Now coming to the third application in organic chemistry, we can identify, or we can check conjugation to study conjugation. That means to distinguish conjugated and isolated dienes. For example, look at this example. This is a diene, isolated diene, where the two double bonds are isolated, and this is a conjugated diene. Actually, this is 1, 2, 3, 4, 5. It is pentadiene, position 1 and 4. Penta 1, 4 diene. This is penta. By noting again the lambda max, which will have higher lambda max. This one higher lambda max. Why? Because it is conjugated, so there is resonance possible, and so lambda max will be more whenever there is more conjugation due to resonance. Here it will be lower value. So that's all about applications in organic chemistry. Now coming to applications in inorganic chemistry, see, in inorganic chemistry also there are applications. That is mainly in coordination compounds. You know that coordination compounds are mostly colored due to DD transition and also due to charge transfer transitions. You know, in a coordination complex there will be a metal, central metal ion and ligands, and in the central metal ion the d electrons, the d orbitals get split into different into two levels, P2G and EG, etc., with a small energy gap. So when light falls, there will be electronic transition taking place. That is called d-d transition, and because of that, coordination compounds are colored. In some compounds, in some complexes, color is due to charge transfer transition. That is, electrons are getting transferred from ligand to metal orbital or metal to ligand orbital. However, by studying the UV visible spectroscopy spectrum or electronic spectrum of coordination compounds, we can study about the nature of metal ion as well as the ligand. it gives a lot of information about the nature of ligand, the strength of ligand. You might have heard about spectrochemical series, which indicate the strength of ligands. Actually, it is established by studying the electronic spectra of various complexes using these ligands. Now finally, application in quantitative analysis. Quantitative analysis. That means we have various quantitative analytical techniques like volumetry, gravimetry, etc. There is another one that is called spectrophotometry, which is based on electronic spectroscopy. Spectrophotometry, there is another name, that is colorimetry. So it is a method of quantitative analysis. It is based on Beer-Lambert's law. Let me put an example. You are given a solution of naphthalene in ethanol, an alcoholic solution of naphthalene. So to estimate the mass of naphthalene, right, in ethanol. Ethanolic solution of naphthalene is given to you. You have to estimate the mass of it. So what are the steps involved? In a few steps you can do this, but you need an instrument called colorimeter or spectrophotometer, which works on the basis of electronic spectroscopy or UV visible spectroscopy. So what are the steps? First thing is, you have to prepare standard solutions of naphthalene. That is the first thing, right? That means you take standard flask, 100 ml standard flask, okay, and you have to weigh out different quantities of naphthalene, pure sample, and prepare solution in alcohol or ethanol. Like you prepare say 0.01 molar or normal, then 0.02, 0.03, etc. You prepare non-concentration or standard solutions of naphthalene, right? Then you take these solutions one by one into the instrument and you measure absorbance of these solutions. See, the basic principle of this method is Beer-Lambert's law, I said, which is represented as A equal epsilon Cx. Epsilon is a constant. For a given instrument, x is also a constant. X is the length of the solution. So the instrument will contain a kind of cuvette, a glass vessel, in which we take the solution to measure the absorbance. So this is x, length of the solution, which is fixed. So these two are constants, so we can write A proportional to C. This is the principle of colorimetry. Absorbance is proportional to concentration. So we have various concentrations of various solutions, and you measure the absorbance of each solutions using the instrument. So you can measure absorbance. Suppose you are getting values like 0.721, then concentration, okay, let it be 0.352, then this is 416, like that it will go 529, like that. When concentration increases, absorbance increase. You get these values. Now what you do is you will draw a graph. You will draw a graph that is called standard curve or calibration curve. A graph is plotted between concentration and absorbance. You will plot this. You will get various points like this, okay, and you will draw a line passing to the origin. You get a straight line. This is called calibration curve or standard curve. Calibration curve. It is drawn, and what is next? Next, what you do is you take the given solution and make it in the standard flask, that is the unknown solution, and you measure the absorbance of the unknown. You don't know the concentration, and you can get the absorbance. So this absorbance you will note in the graph. Correspondingly, you will get the concentration. So this is the concentration required. You get the concentration of the unknown solution from the absorbance. This is how we do this colorimetric estimation, right? So that's all about UV visible spectroscopy. We are left with one more spectroscopy to study in detail, that is NMR, the most powerful spectroscopic technique, NMR spectroscopy, in the coming classes. Till then, bye.